Hi, I'm Casey Steyl.
And I'm Keowa Pretorius.
This is our project on the automated diagnosis of phonocardiograms. My partner and I used signal processing techniques and machine learning methods to develop an algorithm which had 100% accuracy in diagnosing phonocardiograms as belonging to either a normal heartbeat or a heartbeat containing a murmur belonging to aortic stenosis or mitral stenosis. The software was also capable of labeling systolic and diastolic regions within the phonocardiogram, and these were displayed within a developed application. The application had additional features, such as slowing the phonocardiogram and specified region playback. Much of the project's success can likely be attributed to the extracted features, which were specifically designed for this task. The dataset description. In this project, we looked at 3 separate datasets. The first dataset by Yassine Khan contained 1,000 phonocardiograms and was labeled according to the type of murmur present. Dataset 2 by Pascal contained 832 phonocardiograms, and these phonocardiograms were labeled as either normal or containing a murmur. Dataset 3 by PhysioNet contained 3,126 phonocardiograms, and these were also labeled as either normal or containing a murmur. Therefore, for this project, we chose Yassine Khan's database, since our project needed to be able to identify the type of murmur present in a phonocardiogram, not simply whether or not a murmur is present in a phonocardiogram.
Filtering. Noise is a common problem when it comes to any signal processing operation. In the case of phonocardiograms, noise can cause false abnormalities to appear. It is thus very important to minimize the effects of noise. Noise in phonocardiograms can arise from the movement of the patient and other sounds caused by normal functions such as breathing. In this application, a low-pass filter operating with a cutoff frequency of 100 Hz was used. This can be seen in the frequency domain graphs on the left-hand side. The graphs on the right-hand side are phonocardiograms before and after filtering. We can clearly see that the regions of the heart cycle have become more discernible after filtering, and a false abnormality has been removed. Segmentation algorithms. 2 different segmentation algorithms were developed, both with the purpose of locating the starting positions of the systole and diastole regions. The program decides which algorithm to use due to the initial prediction made by the first machine learning model. The first algorithm is used for phonocardiograms of normal heart sounds and mitral stenosis heart sounds, while the second algorithm is used for phonocardiograms of aortic stenosis heart sounds. Both algorithms make use of the MATLAB function findPeaks to determine the initial segmentation locations. The first algorithm used for normal and mitral stenosis phonocardiograms makes use of 3 loops. These loops cluster segments together to reduce the cluster to one location. As we can see here, the cluster of 4 potential peaks have been reduced to one final peak. This is done by clustering together these locations at intervals or tolerances of 8%, 45%, and then 50% of the maximum distance between adjacent segmentation locations. The first segmentation algorithm boasts accuracy of 90.5% for normal phonocardiograms and 96% for mitral stenosis phonocardiograms. The second algorithm, used for aortic stenosis phonocardiograms, makes use of one loop to cluster segmentation locations together and reduce the cluster to 2 locations. These 2 locations are usually the first and last locations in a segment. As you can see on the left, a cluster has been reduced to the starting and ending position for one region. The cluster makes use of a tolerance of 35% of the maximum distance between adjacent segmentation locations. And this algorithm boasts an accuracy of 100% for aortic stenosis phonocardiograms. There are times that the first segmentation algorithm makes incorrect segmentations. This occurs when there are no clear clusters that form from the initial segmentation locations. The program segmentation by looking at the number of regions created, and if an error has occurred, then a second segmentation algorithm is used to create the regions. As we can see on the right-hand side, there are no clear visible clusters, even while looking at a mitral stenosis phonocardiogram. When using the first segmentation algorithm, we can see that a region has been deleted, completely removed. But the same file, using the second segmentation algorithm, correctly locates those region endpoints.
We now move on to feature extraction. Good features are able to distinguish between different aspects of the phonocardiogram well, and this leads to machine learning algorithms with higher efficiency, efficacy, and accuracy. The features in this project were designed to be percentages. This eliminates the effects of differentiating heart rates between the phonocardiograms and keeps features relativistic. So for example, the diastolic segment of a heartbeat might be longer for a patient with a low heart rate than for a patient with a high heart rate. However, both patients may present a normal heartbeat with no murmur. Using the length systole or diastole directly would likely be confusing for the machine learning algorithm, since the lengths of these segments may change based on the heart rate of the individual. However, if we extract a feature which indicates, for example, that diastole is 10% longer than systole, then this would likely be similar for all the heartbeats of a specific class. Additionally, for this project, we extracted 12 features from full phonocardiograms to train machine learning models 1 to identify 3 classes of heartbeat. We also extracted 10 features from models 2 to 4, and these models were tasked with identifying systole and diastole for 3 classes of heartbeat. On the right here you can see the feature importance scores of the different features that were extracted. Machine learning model training. For this project we trained 4 machine learning models, and their confusion matrices can be seen to the right, labeled 1 up to 4. Additionally, we executed a 70-20-10 split on the data. So 70% of the data was set aside for training the machine learning algorithms, 20% was set aside for validating the machine learning algorithms, and then the final 10% was set aside as unseen data to test the accuracy of the diagnosis software. I'd also like to mention that the data was randomly assigned into the 70-20-10 categories. To train the machine learning algorithms, we first gathered a feature matrix which contained all the features extracted from all the phonocardiograms necessary to train this machine learning model. We fed this matrix to the MATLAB classification learner and trained all 32 of the models available there. We would then choose the model with the highest validation accuracy and export this model to be used in our final diagnosis software. We now move on to the diagnosis algorithm. In this project, we used a 4-step process to diagnose an unseen phonocardiogram. In step 1, we used machine learning model 1 to give a preemptive diagnosis of the phonocardiogram. We then use this preemptive diagnosis to accurately segment a phonocardiogram into systolic and diastolic segments. However, since the segmentation algorithm itself is not able to label the segments, we use machine learning models 2 to 4 to label these segments as systolic or diastolic. In step 3, we check how well a systolic and diastolic segment matches a normal heartbeat. So for example, if a segment contains a murmur in it, it will be a poor match for a normal heartbeat, and in this way we can identify it. In step 4, we coalesce all the information from steps 1 to 3, and we output this diagnosis in the form of a sentence. Using these 4 steps, the software had 100% accuracy in diagnosing the unseen data. The output will now be shown in MATLAB. So here we are in the MATLAB program. I have chosen a single aortic stenosis phonocardiogram to diagnose. It is part of the unseen data, so none of the machine learning algorithms have seen it before. And this is the diagnosis software. Let's run it and see what output we get. Alright, so down here at the moment for our output we only have text. So we know that the file that we chose was aortic stenosis. This is just to confirm to the user that this is the file that we chose. The original prediction made by machine learning model 1 is aortic stenosis. S1 likely contains a murmur. This information comes from step 3, where we check the diastolic and systolic segments against diastolic and systolic segments of a normal heartbeat, and we see which one has the least match or the least confidence. And then we just make a short statement indicating whether or not the machine learning model 1 prediction matches the prediction made by the other algorithms. And in this case, it does match. We also output a graph of the phonocardiogram. As you can see here by the legend, S1 and systole are labeled in red, S2 and diastole are in blue, and this just gives the user the opportunity to check if they're happy with the diagnosis themselves by looking at the phonocardiogram and how it was labeled.
The visual application. A goal for the heart murmur diagnosis program was to create an educational tool to train the next generation of doctors. To this end, a standalone computer application was created. The application outputs an interactive graph of a phonocardiogram from a database containing normal aortic stenosis and mitral stenosis files. The visual application includes a help button which explains the working of the application. The user is then allowed to choose the type of phonocardiogram and the file number that they wish to display. The user also has an option of choosing the playback speed of the phonocardiogram. Speeds include normal speed, 75% speed, and 50% of the original speed. The changes to speed does not affect the pitch of the phonocardiogram's audio output. Once the user has chosen, the graph will be loaded, displayed, and played. The green cursor on the graph is connected to the slider below the graph and allows the users to replay the phonocardiogram from a certain location. You can also see that the region that the cursor is currently in is displayed at the bottom of the program. The audio playback speed button makes use of an inbuilt MATLAB function called stretch audio. Stretch audio allows us to slow down or increase the time of any audio file without changing the pitch or frequency of that file, as seen in the video now. These are the references used in this presentation.
The developed program can be considered a success as it boasts 100% accuracy when diagnosing randomly selected testing data. The program's success can be attributed to the combination of feature extraction, machine learning, and signal processing that was used. The high accuracy was ensured by implementing redundancy at every key point in the program to correct any incorrect diagnoses. The program successfully identifies the systolic and diastolic regions of the cardiac cycle. The program outputs results clearly so that it can be used as a diagnostic and/or educational tool. I'd like to end off by giving a big thanks to our supervisor, Professor David Rubin, for his support and guidance throughout this project. Thank you.